Hello everyone. In the beginning of the class, let us see new announcements. Okay, so the first new announcement is May 24th, 2022. Class videos uploaded. Hello everyone. I have uploaded class videos of May 24th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the second new announcement is the slides of chapter 2 has been updated, version 2022-0526. Hello everyone, I have uploaded the latest version of slides of chapter 2 to eCourse 2 website. The location and the file name are eCourse 2 website, wireless communications and machine learning, course content, slides, chapter 2 slides 2022-0526.pdf. Best regards, Wei Zhen. Okay, the third new announcement is the handout of chapter 2 has been updated, version 2022-0526. Hello everyone, I have uploaded the latest version of the handout of chapter 2 to eCourse 2 website. The location and the file name are eCourse 2 website, wireless communications and machine learning, course content, handouts, chapter 2 handout 2022-0526.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class we have taught to chapter 2 handout, page 47, problem 61, solution geometric. Okay, so please open the handout of chapter 2 and search for the word geometric. Okay, so this. Okay, so what are we talking about? Okay, we are talking about the solution to problem 61. What is an exponential family? And in the last class, we have talked about among many others, exponential families includes the following. Okay, and we introduced to geometric distribution. Okay, a number of common distributions are exponential families, but only when certain parameters are fixed and null. For example, okay, first, binomial. Okay, what is binomial? Okay, please, you can click the hyperlink. Okay, problem 62. What is the binomial distribution? Okay, solution. Because of time limitation, I do not plan to introduce it here. Okay, because we have stay on page 47 of the slides of chapter 2. Too much time. Okay. So I think we need to finish page 47, okay, as soon as possible. Okay, with fixed number of trials, Okay, second is multinomial. Okay, what is multinomial? Okay. Problem 63. What is the multinomial distribution? Okay, solution. Because of time limitation, I do not plan to introduce it here. Okay. So with fixed number of trials also. So the third distribution is negative binomial. Okay, let us see the definition. Okay. Problem 64. What is the negative binomial distribution? Solution. Because of time limitation, I do not plan to introduce it here. Okay. Okay, with fixed number of failures. Okay, however, if you have taken the course probability when you are a university student, I think you have been learned what is the binomial distribution. Or if your professor who taught more materials, then you may have learned what is the multinomial distribution. Okay. So notice that in each case, the parameters which must be fixed determine a limit on the size of observation values. Okay, examples of common distributions that are not exponential families are students T. Okay, what is students T? Okay. Oh, sorry. Problem 65. What is the students T distribution? Solution. Because of time limitation, I do not plan to introduce it here. Okay, however, if you have taken the course statistics when you were a university student, then you may learn it in that course. Okay. Most mixture distributions. Okay, what are mixture distributions? Okay. So let us see problem 66. What is a mixture distribution? Solution. Because of time limitation, I do not plan to introduce it here. Okay. And even the family of uniform distributions when the bounds are not fixed. Okay. I think you have learned what are uniform distributions when you took the course probability in the university. Okay, so next problem 62. Okay, we have seen this before. Okay, 63, 64, 65. Okay, 66. Okay, we have already seen this problem and solution before. Okay, so problem 67. What is logarithmically concave? Okay, why do we need to know what is logarithmically concave? Okay, we can search for the word logarithmically. Okay, here. Okay, so we have seen the word logarithmically concave here. Okay, so what is this? Where it is? Okay, so it is the. Okay, let me see. Okay, it is the solution to problem 51. What is maximum likelihood estimation? Okay, so let us go back to the problem. Okay, problem 67. What is logarithmically concave? Solution in convex analysis. Okay, because of time limitation, I do not plan to introduce what is a convex analysis here. A non-negative function f from Rn to R plus. Okay, do you remember what does this mean? Okay, it means there is a function. The name of the function is f, and the domain of the function f is Rn, and the range of the function f is R plus. Okay, what is Rn? Okay, it is the n-dimensional real vector space. And R plus is the set which contains all positive real numbers. Okay, so a non-negative function f from Rn to R plus is logarithmically concave, or log concave for short, if its domain is a convex set. Okay, what is a convex set? Okay, you can click on this hyperlink, and the document, the handout will jump to here. Okay, so problem 6, what is a convex set? Okay, if you forget, please review the solution here. Okay, so let us go back to the convex set we have just seen. Okay, let me see. Okay, there are many convex sets here. Okay, here. Okay, a convex set. Okay, and if it satisfies the inequality f of theta x plus 1 minus theta y is greater than or equal to f of x to the power of theta times f of y to the power of 1 minus theta. For all xy in DOMF, okay, what is DOMF? It means the domain of the function f, and 0 is smaller than or equal to theta, and theta is smaller, and 0 is smaller than theta, and theta is smaller than 1. Okay, if f is strictly positive, okay, in other words, if the value of f is always greater than 0, this is equivalent to saying that the logarithm of the function log circle f. Okay, what does log circle f mean? Okay, it means the composite function of the log function and function f, okay, is concave. Okay, what is concave? Okay, let us click on this hyperlink. Okay, and this handout will jump to here. Okay, problem 60. What is a concave function? Okay, if you forget, please review the solution here. Okay, let us go back to the concave. Okay, we have seen before. Okay, so please recall that. What does mean that the log f is concave? Okay, that is log of f of theta x plus 1 minus theta y is greater than or equal to theta times log f of x plus 1 minus theta times log f of y. For all x, y in the domain of f and 0 is smaller than theta, and theta is smaller than 1. Okay, examples of log concave functions are the 0, 1 indicator functions. Okay, because of the time limitation, I do not plan to introduce what is the 0, 1 indicator function. Okay. However, if you still want to know what is this, okay, you can write an email to me and I will tell you. Okay, of convex sets, which requires the more flexible definition, and the Gaussian function. Okay, what is the Gaussian function? Okay, because of the time limitation, I do not plan to introduce it here. Okay. However, if you still want to know what is the Gaussian function, okay, please send an email to me and I will answer you. Similarly, a function is log convex if it satisfies the reverse inequality. F of theta x plus 1 minus theta y is smaller than or equal to f of x to the power of theta times f of y to the power of 1 minus theta. Okay, for all x, y in the domain of f and 0 is smaller than theta, theta is smaller than 1. Okay. So next, let us see problem 68. What is a score function? Okay. Why do we need to know what is a score function? Okay, let us search for the first time. Okay, that the score function appeared in this handout. Okay, here is the score function. Okay, and where it is? Okay. Okay, we can see that here is the solution to problem 2. What is stochastic gradient descent? Okay, let us go back to the problem about score function. Okay. Solution: because of time limitation, I do not plan to introduce it here. Okay, next problem. Problem 69. What are one-parameter exponential families? Okay, why do we need to know what are one-parameter exponential families? Okay, let us search for it. Okay, here, one-parameter exponential families. And where is it? Where it is? Okay, let us page up. Okay, it is also in the solution to problem 2. What is stochastic gradient descent? Okay, let us go back to the problem. Okay, solution: because of time limitation, I do not plan to introduce it here. Okay, so next, problem 70. What is shuffle? Okay, we have introduced the solution. Okay, if you forget, okay, please review this solution. And problem 71, what is bunch? Okay, we have already introduced the solution to you. If you forget, please review this solution. Okay, problem 72, what is almost surely? Okay, why do we need to know what is almost surely? Okay, let us search for almost surely. Okay. Okay, here, almost surely. Okay, and where it is? Okay, it is also in the solution to problem 2. What is stochastic gradient descent? Okay, let us go back to the problem about almost surely. Okay, solution. Because of time limitation, I do not plan to introduce it here. Okay, so next let us see problem 73. What is pseudo-convex? Okay, so why do we need to pseudo-convex? Okay, let us search for pseudo-convex. Okay, so pseudo-convex is first appears here. Okay, just in the next line to the line which almost surely located in. Okay, so this is the solution to problem 2. What is the stochastic gradient descent? Okay, so let us go back to the problem about pseudo-convex. Okay, solution. Because of time limitation, I do not plan to introduce it here. Okay, so finally, we finally arrive at the last problem of page 47. Okay, it is problem 74. Okay, so everyone, I think I need to tell you an important concept. Okay, so it is important for you to ask questions. Okay, when you learn something. Okay, you can see that we ask 74 problems on page 47 of the slides of chapter 2. Okay, so what is Robbins-Siegmund theory? Okay, why do we need to know this? What is Robbins-Siegmund theory? Where does this come from? Okay, let us search for it. Okay, we can see that Robbins-Siegmund theory just appear in the next line of the line which pseudo-convex appeared. Okay, so let us go back to the problem. Okay, so solution. Because of time limitation, I do not plan to introduce here. Okay, so finally we have finished looking at the handout of the page 47. Okay, you can see that we have spent 1, 2. Okay, so okay, here 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, about 9 classes. Okay, to explain the page 47 of the slides. Okay, I think I could decrease the number of classes on focusing on page 47 in the next year's class. Okay, so next let us go back to the slides, and please turn to page 47. Okay, so ultimately we have introduced what is a stochastic gradient descent method. Okay, it is a very long introduction. Okay, so let us go to next page an alternative approach is to estimate together the, okay, it is 25 minutes. Let us take a break.